Hello children, how are you all? Hope you all are fine and doing well. My name is Naresh. Welcome to our channel Physics Plaza. Children, in today's session we are going to start a new chapter, work, power, energy. And in this session just we are going to discuss what is a work, what are the units of work, and some special cases in that, when the work done is 0, when the work done is positive, now when the work done is negative. These things only we will be discussing. Children, before going to discuss, let us have a look here. It is a work, power, energy. One similarity is there between this work, power, energy. What is that? These three are scalar quantities. These three are scalar quantities. It's very important, dear children. These three are called scalar quantities. What is scalar, dear children? A quantity should have only magnitude but not direction. Am I right? But then what about electric current? It has a direction and a magnitude also. When sometimes we cannot say only with the direction we will decide whether it is a scalar quantity or a vector quantity. It should obey the law of vector addition. So what is a vector actually? The quantity should have a magnitude and a direction, at the same time should obey the law of vector addition. But whereas scalar means it should have, sometimes it may have only magnitude, but sometimes it may have even direction also, like electric current. But if it is not obeying the law of vector addition, that we can call it as a scalar quantity. Anyhow, we will discuss about scalars and vectors in detail in further sessions. Okay. Today let us see what work actually. Children, what do you think about work when you can say that work is done? In fact, dear children, we are very familiar with this term called work. So some other way daily, since morning to evening we can hear. Of course, we also feel that we are doing so much of work. In fact, the basic example I'll tell you. One person is sitting in front of a laptop, is doing his project since morning to evening, continuously hours and hours, without having food and any drink also. Continuously is like sitting and doing a work. Of course, at the end of the day, he thinks that he has done so much of work. But dear children, scientifically, he has done no work actually. Why? Because let us discuss that also. Even let us take a case of a taxi driver. He is sitting in a car, continuously driving. Of course, he is doing so much of hard work since morning to evening. But at the end of the day, of course, he feels tired and he thinks that I did so much of work. But really, did he do the work? Let me give you one more example. Here is a wall. Let us take this board. If I go on pushing it, dear children, I'll apply so much of efforts. Putting so much of efforts. 1 hour, 2 hour, 3 hour. Continuously if I'll do like this, definitely I'll get tired. But what I feel, what I think that, my God, I have done so much of work, but I could not make the wall to move. Children, in all these cases, work is not done actually. So in our daily life, whenever we feel tired, we think that we have done work actually. But scientifically, according to physics, when you can say that work is done? Let us see here. For suppose, dear children, let us take, here is an object, it is at a point A. Okay. On this body, a force of F is acting, a constant force. Children, a constant force acting on this body continuously, let us think. Then what will happen? This body is displaced, let us suppose. This body is displaced. So that it is moved from point A to point B, so that there will be displacement S. Then we can say that some work is done. This force has done some work. Which means what? It does not mean that only force is acting on a body so that work is done. It is not that, dear children. So force should act on the body, and at the same time, there should be some displacement. Then only we can say that some work is done. So how to define work done? Work is said to be done by the force when it displaces the body. When it displaces the body, then we can say that some work is done actually. But dear children, do you think that always body is displaced in the direction of applied force? Of course, may or may not. Come on, think once. In which case, body is not moved in the direction of applied force. No. We think that, no sir, whenever we are pushing something, the body also displays in the direction of force only. But how can you say that body may not be displaced in the direction of applied force? We will discuss that. Before that, let us discuss the units of work actually. Let us see. So mathematically, how can we write actually, dear children? So work can be written as force into displacement. Force into displacement. Children, it is a purely product only. It is not cross product. It is okay. Let us see. What are the SI units of work? Children, if before going to write the units of work, we must know what are the units of force, what are the units of displacement. Children, what is the SI unit of force actually? Let us see, children. Actually, force is equal to, according to Newton's second law of motion, we got F is equal to ma, right? So here mass is measured in kg. Mass is measured in kg. The acceleration is expressed in terms of meter per second square. So the SI unit of force is kg meter per second square. So children, this is only we can call it is given as a name Newton. It is only we can call Newton, symbol we can write capital N. So the SI unit of force is Newton. Then what about CGS unit? Let us see. The CGS unit of force. So if you want to know the CGS units of force, let us take again same formula MA. Mass is measured in grams in CGS system. Acceleration is centimeter per second square. So now let us write the units for force, dear children. So what are the units of force here? Gram, centimeter per second square. Very simple, very simple. Let us not by heart this. Centimeter per second square. So children, this gram, centimeter per second square we can call it as a dyne. So now this SI unit and the CGS units are very useful to us to write the units of force, units of work actually. So now in order to write the SI units of work, dear children, so let us take SI unit of force is what? Newton. The SI unit of displacement is meter, of course. So as force is measured in Newton and displacement is measured in meter, then the work units are, it is Newton meter. Children, so what is the SI unit of work here? Newton meter. Children, this Newton meter only we can call it as a joule. Joule, capital J. It is simple. So children, now onwards we can refer what is the SI unit of work. The SI unit of work is joule. What is joule here? Newton meter. Newton meter. Now what are the CGS units of work? Let us see. CGS units of work, children. What are the CGS units? In the CGS system, the units of force are dyne. The force is measured in terms of dyne, whereas displacement is measured in terms of centimeter. Then work is measured as it is a force into displacement, so it will be dyne into centimeter. It will be dyne centimeter. Children, this dyne centimeter only is given special name. Dyne centimeter only is given special name called erg. It is called the erg. So the SI unit of work is joule. The CGS unit of work is what, dear children? Erg. Now let us see how a joule and erg are related. It's a very, very important. In examination, they'll be asking you 1 joule is equal to how many ergs, or 1 erg is equal to how many joules. Even children, before going to learn the relation between joule and erg, let us see what is actually joule. How can you define the joule? What is actually erg? Let us see. Children, how can we define the joule? It's very, very important. What is joule and define the joule? It's very, very important question actually. Children, here suppose here is a body is there here. Let us suppose a body is placed at a point A, so that here is placed in a horizontal. Fine. And here, children, here the force is acting. A force of 1 Newton is acting. A force of 1 Newton is acting, so that the body is displaced through 1 meter distance. Through 1 meter distance. Try to understand, children. So here a force of 1 Newton is acting on the body, so that it is displaced through a displacement of 1 meter. Then the work done by the force is called as 1 joule. Work done force is called 1 joule. If force is equal to 1 Newton and displacement is equal to 1 meter, then, dear children, work is called actually 1 joule. Children, work is said to be called 1 joule. Work is said to be equal to 1 joule when if 1 Newton force acting, what are the 1 Newton force acting on the body should displace the body through 1 meter displacement. Then the work is said to be done 1 joule. Now what is erg here? What is erg here? Let us see. Children, same concept it is, same concept. So let us take, here is an object. So on this, one dyne force is acting. And what are the one dyne force acting on the body? If it displaces the body through 1 centimeter distance, then the work done by this force we can call it as a 1 erg. Force is equal to 1 dyne, then displacement is equal to 1 centimeter, then W is equal to 1 erg it is. W is equal to 1 erg. Children, I repeat once. Work is said to be done 1 erg when if one dyne force acting on the body displaces the body through 1 centimeter distance. Children, as it is like a straight line motion, as I considered along the straight line, I am using displacement distance in a similar manner. Don't get confused. In a one dimensional motion, displacement distance both are same one. So children, this is how actually we can define joule and we can define the erg also. Now let us see the relation, how erg is related to the joule. So now let us see how a joule is related to erg. 1 joule is equal to how many ergs, or 1 erg is equal to how many joules. Let us see, children. So here, children, we know that 1 joule is nothing but the Newton meter. So this Newton meter only we can call it as actually joule. Children, if you want to make a relation, you must know how Newton is related to the dyne, how meter is related to the centimeter. That's very important. Children, we know that 1 Newton is equal to 10 power 5 dynes. But how? Children, you learned in the previous sessions. Forgot? Let us see once in a simple manner. I'll tell you. Children, Newton is what actually? Kg meter per second square. We know that. 1 kg is equal to how many grams, dear children? 10 power 3 grams. 1 meter is equal to how many centimeters? It is 10 square centimeters per second square. So this will be 10 power 5 into 10 power 2. It will be 10 power 3 into 10 power 2. It will be 10 power 5 gram centimeter per second square. But this gram centimeter per second square only we can call it as a dyne. So here 1 Newton is equal to 10 power 5 dyne. This is how actually we got. So we should know that 1 Newton is equal to 10 to the power 5 dyne. Children, this is actually what? Dyne. So 1 Newton is equal to 10 power 5 dynes. And we know that 1 meter is equal to 100 centimeters. That we can write 10 square centimeters. So look at here. So in the place of Newton, children, we can write 10 power 5 dynes. 10 power 5 dynes. Whereas 1 meter equal to 100 centimeters. That is 10 square centimeter. 10 square centimeter. Children, have a look here. This we can write 10 power 5 into 10 power 2 dyne centimeter. 10 power 5 into 10 power 2. It will be 10 power 7. It will be 10 power 7. Dyne centimeter is called actually erg. So it is erg. So children, 1 joule is equal to we will get as a 10 power 7 erg. It's very, very, very important, children. Don't get confused, children. 1 Newton is equal to 10 power 5 dynes. And 1 meter is equal to 10 square centimeters. So substitute in the place of Newton 10 power 5 dynes. In the place of meter, just you substitute 10 square centimeters. Then we will get it as a 1 joule is equal to 10 power 7 erg. Or we can write it like this also. Or we can write 1 erg is equal to 10 power minus 7 joule. It is 10 power minus 7 joule. Children, this is how actually joule is related to the erg. You can write 1 joule is equal to 10 power 7 erg, or even we can write 1 erg is equal to 10 power minus 7 joule. Okay, children, this is what actually work done and the work formula, what is a joule, what is the erg, and how they are related. But dear children, do you think that always the body is displaced in the direction of applied force? Children, in generally we may think, of course, yes, like that you may think. But dear children, it is not compulsory. Always body is not displaced in the direction of applied force. If body is not displaced, children, till now we discussed W is equal to force into S. When we should use that formula, actually a constant force should act. Okay, that formula is used only when the body is displaced in the direction of applied force only. Then we get a one doubt. Sir, If not, if body is not displaced in the direction of applied force, then how to calculate? Yes. Now children, we are going to discuss how can we calculate the work done if the body is not displaced in the direction of applied force. Means it is not compulsory that force and displacement always should be in the same direction. If not, what will happen? How to calculate? What are the factors which affects? Let us see, the children. For suppose, dear children, let us take here is horizontal here, and you might be seen that a rolled roller, not a rolled roller, dear children. So even during the cricket match also, between the gaps of the overs, they'll be cleaning the pitch with a roller. Okay. So here the person, it is being pulled like this, children. Here is a handle. Here is a handle. So they'll try to pull like this actually. They'll try to pull like this. But dear children, do you think that the roller will go in the direction of applied force only? Of course, no, it won't move. So this roller will move like this actually. Even not only this, dear children, even you can take a situation where the briefcase with the wheels will be, how can we pull actually? Let us take this. So for suppose here is briefcase. It has some wheels. Let us suppose. So it is something will be like this. Something it will be there. So we will be pulling like this. Okay, now but it will be moving like this. I mean, we cannot pull like this, we cannot pull, right? Certain angle on we will be pulling here. So this is what actually we will be pulling, but this is actually what direction, in which direction the briefcase is moving actually. So same case here also you can take here. So here force is acting in this direction, but here body is moving in this direction. So it is a displacement. So children, so there will be now angle. Let us say the angle is theta. So in this case, then how to calculate the work done? In this case, how to calculate the work done? So children, here only we are going to use the vector concept actually. So as we know that any vector can be resolved into two rectangular components. So according to that concept, so force horizontal component will be F cos theta here, F cos theta, and here vertical component of the force will be F sin theta. This will be F sin theta. So then here, which component of the force should be considered? Should we consider F cos theta or F sin theta? We should consider the component of the force which is in the direction of displacement. I'll tell you one thing, children. Okay, let us suppose take, sir, here F sin theta also component of force only, F cos theta also component of the force only. Why we should consider only F cos theta means I'll tell you. Children, this F sin theta is balanced by weight. According to Newton laws actually, this F sin theta is a balance with this weight of this roller here. Means what will happen? This component of the force cannot make the body to move. So do you think that the body can move like this? No, it is not that. So it does not show any effect here, because the result, the net will be 0 here. Net force will be 0 here. But whereas here, F cos theta is responsible. So F cos theta will make the body to move. So that's what we are saying, that we will consider the force component which is in the direction of displacement, that is F cos theta. So we know that work is equal to force into displacement. We know that work is equal to force into displacement. Force means we have taken the force component of the force which is in the direction of displacement, that is F cos theta, and it is displacement. Yes, only it is a displacement, children. So this will be F cos theta into displacement. This we can write as a F S cos theta. F S cos theta. Children, according to the concept of dot product, we have this formula. What is that? If A and B are two vectors, then A dot B is equal to, we can write as A B cos theta. That is, A, B are the magnitudes of the cos theta. So means these are the two magnitudes and here is a cos theta. So this can be written like this. Am I right? So according to that concept only, so this can be written here F dot S. So children, actually remember that work is not actually F into S. It's very important. It is a F dot S. Children, here one more very important point. Very important. What is that? The dot product of two vectors always gives scalar quantity. It's very important. Children, F is a vector quantity, S is a vector quantity, this is a displacement vector quantity. But here work is a scalar quantity. Children, it is one of the important properties of actual dot product which we will be learning in further sessions, that the dot product of two vectors is always scalar quantity only. Children, this is how actually we can calculate when body is not displaced in the direction of force. Of course, even we can calculate by taking the displacement component of the displacement we can take. It is not compulsory that always we should take a force component only. Okay, we'll see one more example, where we can, in this also we can actually, but we'll see in one more example how we can consider the displacement, what we can say component. For example, dear children, let us take here is a inclination like this, it is there, let us say it is a inclined plane or something like this, inclination, let us say A, B, C. So here an object is there like this, object, okay now. So on this object, a constant force is acting like this, F is a force acting, let us say. So what will happen? Do you think that this body will go horizontally? Of course no, force is acting horizontally, but body cannot move horizontally. What will happen? It will go along the inclination. It will go along the, let us suppose it has moved from here to here, let us suppose. But still here force is acting, dear children, still here force acting continuously as I told you that. Then what will happen? Still it is raised. Let us say the body has moved till the end of the edge at this point B, let us take till here. So here the force is stopped, let us say. Means in this case a force is acting so that there will be some displacement. But how can we calculate the work done here? Because body is not displaced in the direction of force. Body is not displaced in the direction of force, then how can we calculate? Let us see, dear children, here. So this will be the angle theta. This is the angle theta between force and displacement. Let us say, dear children, this total displacement AB is, let us say it is S only. It is S. It is S. So children, just now what I have told you that vector can be resolved into two components, rectangular components, horizontal component and a vertical component. Children, here the horizontal component of displacement will be S cos theta, whereas its vertical component will be S sin theta. S sin theta. Then again we will get a doubt, sir, which component of the displacement should we take? Should we take S cos theta or should we take S sin theta? Children, we should consider the component of the displacement in the direction of force. So do you think that S sin theta is in the direction of force? Of course no here. So S cos theta is in the direction of force. So let us see here. Work is equal to force into displacement S cos theta. So according to the property, dot product, as I told you that Fs cos theta can be written as a F dot S. It is F dot S. So children, this is what actually finally we will get the expression. So work is equal to the dot product of force and displacement. Children, either you can take a force component or you can take a displacement component. Anything is okay. We will get the same expression. Children, I repeat once. So if body is not displaced in the direction of applied force, then what we should do actually? So we should go for the concept called resolution of vector. So there we should consider either component of the force in the direction of displacement or component of the displacement in the direction of force. Actually we have to calculate, and this is how actually we can do. Please copy it. Children, now let us see some special cases when the work done will be positive, when the work done will be negative, when the work done will be 0 actually. So before going to that, dear children, on which factor does the work done depends? Very important. Children, this is what actually final expression we got. W is equal to F S cos theta. So it's very important. So with the help of this only we can say when the work done is positive, when the work done is negative, when the work done is 0. Children, work done depends on three factors. It's very important. Work done, please note down. Work done depends on the following factors. What is that? First one is it depends on the magnitude of force. Whereas second factor is that displacement. Magnitude of displacement, children. Magnitude of displacement. And third one is what, children? The angle between, very important, angle between force and displacement. Children, these are the three factors on which work done depends. So whether work done is more or less, whether it is a positive or a negative 0. So with the help of these three factors only we can say. Children, now let us see this is a case 1. Children, let us take a case where a body is falling freely like this. A body is falling like this, freely falling body. Let us take a freely falling body, and here is a earth surface. Let us say here is. Children, what will be the direction of gravitation force? Of course, gravitation force will be acting downward only. But what will be the displacement direction? Of course, it is downward direction only. Children, F is a gravitational force. S is a displacement of this freely falling body. Displacement of freely falling body. Just try to see the directions. Children, force is acting vertically downwards only. Displacement also is vertically downwards only. So, can I say that both are in the same direction? Yes. So, both are parallel. Both are parallel. So, both are in the same direction. Then what will be the angle between force and displacement, children? The angle between force and displacement is 0 degrees. 0 degrees. Okay, children? Fine. Now, let us calculate in this case what will be the work done. So, we know that W is equal to here F S cos theta. In the place of theta, what we should write? 0 we should write. That is cos 0. Children, cos 0 value will be how much? It is a 1. So, finally we will get W is equal to Fs. W is equal to Fs. So, means what, children? F is a positive only. Here displacement is positive only. So, then work done will be positive only. So, when the work done will be positive, children? When the body is displaced in the direction of force. Body is displaced in the direction of force. Means force and the displacement both should be in the same direction. Then the work done is positive. And children, it's very important here. Work done by whom? Who is doing the work here? We are talking about the work done by gravitational force. Children, it's very, very important. Who is doing the work is very, very important. We have to specify that. In this case, the work done by the gravitational force is a positive. Okay. Let us see one more case. Case 2. Case 2. Children, in this case, let us suppose a body is thrown vertically upwards. A body is thrown vertically upwards, let us suppose. So, in this direction. But gravitational force will be vertically downwards only. But in which direction the body is displaced? Upward direction. So, the displacement will be upward. But the gravitational force is vertically downwards here. So, now what will be the angle D, children? Look at here. So, here this is what actually force direction, and this is what actually displacement. So, body is going vertical upwards. So, children, here is both are opposite. Here is angle is 180 degrees. 180 degrees. Then in this case, how to calculate the work done and what will be the work done? Let us see once. Children, we know that it is W is equal to Fs cos theta. In the place of theta, now let us write 180 degrees. That is cos 180 degrees. Children, but cos 180 degrees is a minus 1. Cos 180 is a minus 1. So, it is W is equal to minus into Fs. This will be minus Fs. Look at here. So, W is equal to, we got minus Fs. Children, here work done is negative we are getting. Work done is negative. So, when the body is displaced in opposite direction to the applied force, then the work done will become negative. Children, in this case, the work done by the gravitational force is a positive. In this case, the work done by the gravitational force is a negative. Actually, children, you may get one doubt. Sir, who is throwing vertical upwards? Of course, some person only throwing. Then what is the work done by that person? Yes, children, it's a very good point here it is. So, if for example, in this case only, here one fellow is there. So, here is a fellow, he is throwing ball upward. Means he has to apply the force upwards only. He has to apply the force upward direction only. Of course, in this case, the work done by the person will be positive. Children, it's very important. Don't get confused. That's what I said. You have to specify work done by which force is very important here. In the same situation, I can talk about work done by gravity, work done by the person. Children, if I can talk about the work done by gravity, as a gravitational force is acting vertically downwards and the body is displaced vertically upwards, then both are opposite in direction. Then the work done by the gravitation force is a negative. But when I consider the force applied by the person, so here person, let us say I am the person, just I am applying force like this, zoom like this. I am applying the force like this only. So the body is going upwards only, I am applying the force also vertically upwards only. So in this case, force and displacement both are in the same direction. So work done is a positive. Children, it's very important. work done by gravitational force is a negative, but whereas work done by the person is a positive. Why? Person is applying force in the same direction of displacement, means body is displaced in the direction of force applied, whereas in this case body is displaced in the opposite direction of the applied force. Okay children, so this is what actually we can say how work done is a positive, how work done is a negative. Now let us see in which case work done will be 0. Children, now let us see case 3 is a very simple, very important. Let us see. So in this case we are going to discuss when the work done is going to be 0. Very simple. When the work done is going to be 0, children? If we cannot apply the force, the work done is 0 only. Children, no force, no work done, no study, nothing. No need to learn about even units of work only. Okay, it's not like that. Let us see, children. So W is equal to Fs cos theta. For suppose, let us take if force only 0. For example, children, I am simply standing like this. What is the work done by me here? I am not applying force. I am not at all applying force, just I am standing. So, as I am not applying any force, definitely there won't be any work done, right? So, that's what. So, as F is equal to first division, so here F is equal to 0, you can substitute. Then 0 into something will be 0 only. So, that is equal to 0. Of course, no force, no displacement, that's it, it's 0 only. Okay, fine. So, then can we say that some force is acting on a body means definitely will do some work? Of course, it is not that. The best example, just as I told you, children, I go on pushing this wall like this. I am applying, let us say 50 Newton, 100 Newton, example. But still, I cannot make the wall to move, right? So, what is the force which is acting on the wall? It cannot produce any displacement. Means what? Displacement is 0, yeah, it is a displacement is 0. Force is acting, but still displacement is 0. So, let us see. So, here, force is not 0, but displacement is 0. But okay, no need to take a vector notation here. Displacement is 0. So, then also in the place of S you can substitute 0. Then it will be W is equal to work done is 0. Children, no force, no work. Force is there, force the hai, but there is no displacement. So, work done is 0. Yes. Now, let us see. Yes. Children, let us take one more case here where nice. Let us take here is one car. Let us take here, vehicle is going like this, zoom, zoom, zoom. Yes, let us take it's a car. What is that car? Ambassador. Okay, let us see. One car is going. So, let us say the displacement. So, the car is going in this direction, children. So, this is the displacement of the car. And what will be the direction of gravitational force there, children? The gravitational force, gravity is pulling downwards. So, gravitational force acting downwards. Yes. Now, of course, now children, force is not 0. Okay. Displacement is not 0. Okay. But can we say that work is done? Come on, think. We have to think about the angle also. We discussed already. Work done depends on 3 factors. One is force, magnitude of force. Another is displacement. Third one is the angle between the force and displacement. Look at here. What is the angle, dear children, here? The angle between force and displacement is how much? It is 90 degrees. Look at here. So, this is what actually? 90 degrees. So, what, sir? Let us see mathematically what will happen here. So, children, here W is equal to Fs cos 90 degrees. Children, cos 90 degrees value will be 0. So, 0 into Fs will be 0 only. 0 into Fs will be 0 only. Children, scientifically, it is not that if force is acting and there is a displacement, then we can say that work is done, some work is done. It's not that actually. So, the angle also matters. Children, here strictly I am talking about work done by the gravitational force. Please note down that. Then if you can think work done by the engine, yes, it is doing work. So, that only body is moving here. That is okay. But strictly I am talking about what actually? Work done by the car. Work done by the, gravitational force. So, work done by the gravitational force. This force is perpendicular to the displacement. So, I can say that the work done by the gravitational force. Children, mentioning a force is a mandatory. Work, who is doing the work, which force is doing the work is very important. We have to mention. When I took a case 1, there a ball is like it's freely falling. There we discussed the work done by the gravity is positive. In the second case, where a ball is thrown vertical upwards, ball is going vertical upwards, the gravitational force is acting vertical downwards. So there work done by the gravity is negative. But in this case, again work done by gravity only we are thinking. Work done by gravity is 0. Children, this positive, negative, 0, you know, this we can show in a same one example only. How? Let me give you clarity here. Very simple example we can show that. For suppose, dear children, here, you know, let us take one box. Let us take one box. Nice box you can take. Yes. Let us take some rectangular box is placed on a horizontal surface. Okay, children? Fine. Now, on this body, let us say a force F is acting. External force F is acting. External force F is acting. Let us say F is acting, dear children. So that body is displaced. Okay. Body is displaced from here to here. Let us suppose. As a body is like a displaced, as a body is moving, dear children, a kind of force will come into play which always tries to oppose the motion of the body. What is it called? Frictional force. So what is the direction of frictional force? Children. So the direction of frictional force will be like this. Always opposes. Children, remember that. Body is displaced in this direction. So this is how actually body is displaced. This is a displacement. Children, it is external force. Here is what actually force of friction. And don't you think that the gravitational force also will be acting in the body? Of course, yes. The gravitational force will be acting here. Let us say. So let us say the gravitational force is a Fg. So children, here three forces are acting. External force, frictional force and gravitational force. Children, with this simple example, we can understand better way that when the work done is positive, when the work done is negative, when the work done is 0 actually. Very simple way we can understand. For suppose, dear children, here, now I want to calculate the work done by external force. Work done by external force. So let us take Fs cos theta only. So as a body is displaced in the direction of applied force, so theta will be 0. So then it will be Fs cos 0 degrees. So it will be Fs only. So here work done by external force is, children, positive. Work done by external force is positive. Now I want to calculate the work done by the frictional force. Let us see. Work done by, children, it is frictional force. Work done by frictional force. Look at this. So friction is acting in this direction, but whereas body is displaced in this direction. So both are opposite direction. So it will be Fs cos 180, opposite 180 degrees here. So cos 180 will be how much? Minus. So it is minus, sorry, here F should be small. Friction force, right? It is minus Fs. So in this case, work done by frictional force is negative. Work done by frictional force is negative. Now what about the work done by the gravitational force? Children, body is displaced horizontally, but the gravitational force is acting vertically downwards. Then what is the angle between these two? It is 90 degrees. So work done by the gravitational force is equal to Fgs cos 90. Children, cos 90 will be how much? It is a 0. So 0 into Fs will be 0 only. So work done by gravitational force is 0. Children, look at here. With a single example, we can understand three cases when the work done is positive, when the work done is negative, when the work done is 0. It's a very important. So children, this is what actually today we wanted to discuss here. So what we have learnt in today's session, dear children? In today's session, we discuss what actually work is. What is work? What is work? When the work is said to be done, when the force is acting on a body and it displaces the body in a means in the direction of force applied actually. Then we can say it is a work done. Then we discuss the units of work. The SI units of work is joule and the CGS units of work is erg. And 1 joule is equal to 10 power 7 erg. After that we discuss in which case actually work done will be positive, in which case work done will be negative, and in which case work done is 0. So children, it's very important. These are the 3 special cases under what work which we have learnt actually. In next session we will be discussing what is the power and what is the energy, and how power and work are related. Then we'll do the related numericals. Thank you so much dear children, all the very best.